Hey guys, welcome to the flight dynamics course. Today we're going to see the topic on coupling between rolling moment and yawing moment. So this is the coordinate operation of airplane during the flight. One is the aileron and the rudder controls usage. So introduction to the coupling of rolling and yawing moment. Rolling and yawing moment is an aircraft are interconnected, which influence the lateral and directional stability. Coupling refers to the interaction where one type of motion induced or affect the other one, like rolling affect the yawing. In many aircraft, rolling tends to induce a yawing moment and vice versa during aerodynamic forces. Understanding this coupling is critical for maintaining rolls, especially in high performance maneuvering. Engineer designs of aircraft to manage this interaction for safe, stable, and responsive handling. The fundamentals of rolling moment is the torque that causes the aircraft to rotate around its longitudinal axis. The roll is primarily controlled by the aileron, creating a lift differential across the wing. The amount of rolling moment affects the roll rate, influencing how quickly the aircraft is banked. Rolling moment is affected by wing configuration, speed, and control surface deflection. The rolling moments can interact with other forces, producing an unintended yawing response. Coming to the fundamentals of yawing moment is a torque causing rotating about its aircraft vertical axis. Yaw is mainly controlled by the control surface rudder, which generates a side force to rotate the aircraft left or right direction. Yaw moments influence the direction of flight and crucial in coordinate turn, as with rolling and yawing is impacted by aircraft speed, control surface deflection, and airflow. Yawing moments often lead to roll due to asymmetric lift and other aerodynamic forces. So, aerodynamic factors leading to this coupling action: when an aircraft rolls, wing experience higher lift, also experience greater drag. This differential drag causes adverse yaw, a yawing moment opposite to the roll direction. Similarly, when an aircraft yaws, the outer wing experience a faster airflow, which including rolling moment. Differential effect or diagonal effect and the wing sweep also enhances the natural coupling between row and yawing moment. These aerodynamic four factors make it essential to design for controlled coupling effect and the adverse yaw and the rolling yaw coupling. Adverse yaw is a naturally byproduct of roll where the aircraft yaw is opposite direction of roll. This coupling is due to increasing drag on the upward deflection aileron wings. Adverse yaw complicated turns requiring rudder input to keep turns or coordinate turn. Effective coupling management, which reduces adverse yaw for smoother and controlled flight operation. Recognizing adverse yaw role is crucial for pilot to maintain directional control in coordinate turn. The role of diadral in row yaw coupling: diadral angle, the upward tilts of wings naturally stabilizing rolling, which the turns the aircraft in the level flight. Diadral effect causes the aircraft to yaw back to center in response to the roll, linking roll and yaw movement. This coupling effect contributes to lateral stability but can reduce maneuverability in sharp turn. Higher diagonal enhances stability but may require more rudder input to counterattack coupling in coordinate turn. Understanding this diagonal effect on roll yaw coupling aids in achieving desired stability characteristics of airplane. Effect of wing sweep on roll yaw coupling. Sweep back wing influences coupling by creating a natural roll response during yawing. The outer wing is a yard position counteracted more airflow, generating additional lift and the additional roll. This is the roll yaw coupling due to wing sweep weight stability, partially in higher speed aircraft and higher aspect or higher sweep angle often enhance stability but can make the aircraft more challenging to control precisely. Wing sweep is a design consideration in managing roll yaw coupling, particularly for stability at higher speed operation. Spiral instability and roll yaw coupling. This is a dynamic case. The spiral instability occurs when the aircraft motion generally increases due to insufficient roll damping. In spiral instability aircraft, roll yaw coupling causes a slow roll to develop into a more server yaw. This coupling can lead to an uncontrollable spiral dive if not corrected by the pilot. Designer adjusts diameter and sweep to balance coupling, minimizing spiral instability during dynamic operation. Recognizing spiral instability, which helps to pilot to apply corrective input to maintain aircraft in a safer flight. So coming to controlling roll yaw coupling with rudder aileron coordination. So both the rudder and aileron helps to control the roll yaw coupling. The pilot can use coordinated rudder with aileron, which inputs counter adverse yaw and manage coupling. Proper coordination, smoother turns, reducing uninterrupted yaw or roll for coupling effect. Flight control system is moderate aircraft helps automated rudder aileron coordination. Integrated control minimizing the effect of roll yaw coupling for a more stable flight experience. Mastering of coordinate skills is essential for safe and efficient flight, particularly in crosswind or turbulence landing. Coming to the conclusion, managing roll yaw coupling in a flight dynamics, roll yaw coupling in a fundamental aerodynamics interaction that affect stability and maneuvering. Proper aircraft design consider wing configuration, diagonal, and the control systems integration to the managed coupling operation. Flight dynamics required balancing roll yaw coupling to achieve stability without sacrificing maneuverability. Pilot plays a key role in managing coupling through coordinates input, especially in adverse yaw condition. Understanding and managing roll yaw coupling is essential for both engineers and pilot to ensure safe and responsive flight operation. Thank you. We'll see you in the next class.